Hello everyone. So in this video, let's discuss what is Gauss law and what it can tell us about the electric field and the electric charge. So to learn Gauss law, we have to learn a concept called electric flux. So let's start with a simple case. You just have an area and then you have an electric field pointing perpendicular. So the field itself is perpendicular to the area, this red area. And in geometry, there's a way we can define the norm vector of the area. We call it vector A. So in this case, the direction between E and A is 0. And to visualize it, you can see you have electric field length. Now in this case, you have none electric field length. And they are all going through this area. So electric flux is basically can be visualized as how many electric field lengths you have going through an area. So if you have more electric field lengths going through an area, you have more electric flux. Now, it doesn't have to be that your area is exactly perpendicular to the electric field. It can have an angle, and in such a case, you need to calculate your electric flux. Taking into consideration of this angle as well. So the equation is going to be, you need to find the angle between the normal vector of this area. You need to find EDA, this A, and the angle between them. So your electric flux is calculated as E times A times cosine phi, the angle between A and E. So you can interpret it as, you have two areas. You have this area, which is a projection of area A in this direction. The electric flux going through this area and the electric flux going through this area, they are equal because you can count there are same number of electric field lengths going through these two surfaces. If your surface is exactly in the direction of the electric field, so if in this graph your E, all the E electric field length is in the same surface, which means the norm vector of this surface A has an angle 90 degree with E. You have the E and A 90 degree, cosine 90 degree is going to give us 0. So electric flux in this case is 0. And visualize it, you don't have any electric field length penetrating this area or going through the area. So there is no electric flux in this case. For a more complicated area and the electric field configuration, we need to do integration. So more rigorously is written as E dot product A, and then you integrate over the area. So for a very small area, at least, you can still use what we learned, E times area times cosine the angle between E and A. And the SI unit for electric flux, because this unit should be E, same as E times A, the unit for E, SI is Newton per Coulomb, A is area. So this is a unit for electric flux. Now let's think about the electric flux of a point charge. So if you have a point charge, so by Coulomb's law, we know the electric field for this distance r. What will be the magnitude of the electric field here? Is k times q over r squared. There's the electric field here. Now you keep this solid angle, we call it a solid angle, and then you go to another sphere which has a radius 2r. What's the strength of the electric field here? Electric field here, let's call it 2r, and then we call this one ER. E2r is K times Q over 2r squared. So you will find out electric field at 2r surface is 1/4 of the strength of ER. Now, what is the area? This dA for sphere radius r, and then this dA for sphere radius 2r. How the area compare? And we can find out because area of a sphere, and it's even for the element goes as r squared, right? And you double the radius, the area quadruple. So the area here is 4 times area here. Now, did you find something? Electric strength here is 4 times larger than electric field strength here. Area is 1/4 of the area here. So if you have a product of E times A for this one and this one, electric flux is the same. So electric flux is independent of the sphere you choose, at least for this program. And this electric flux through an area, it doesn't even have to be a sphere, it can be any shape. And how do we argue it? So you keep this solid angle, here. The electric flux going through this sphere area is going to be the same as any shape of area you have here. You can cut an irregular area to a lot of these kind of shapes, and the electric flux will always add up to those electric flux going through this surface area, right? And you add everything up, you find the electric flux going through this area still equals to the electric flux going through a very, very regular sphere. The argument is you need to do the projection. So this irregular piece of area, the electric flux, based on the definition, is going to be the same as the electric flux going through this regular piece of area. So we found out it is, at least for this point charge case, electric flux is independent of the surface of your choice. So what does it depend? And this basically is Gauss law. Gauss law tells us this is a special case of Gauss law. So if there is no charge in the Gaussian surface, like this one, so you have a charge here, you have a Gaussian surface, and at the beginning I kind of make a statement that the electric flux would be equal to how many electric field lines going through the area, right? And now it comes to, we need to define what's the positive electric flux, what's the negative electric flux. And we have a Gaussian surface like this, so we have to define the area. The positive area is pointing out of this closed Gaussian surface. So area is pointing out here. Area is pointing out here. And your E in this side, on this side, is in the opposite direction of your dA. So electric flux here is positive. All here is positive. Electric flux on this side is positive. And we said you can equal electric flux to how many electric field lines are penetrating this surface. If you don't have any charge, by top notch, we can prove that you always are going to have equal numbers of electric field that goes into the surface compared to the electric field that goes out of the surface if you don't have any charge inside the Gaussian surface. So we can make a statement: the electric flux is 0 and you don't have any charge. So we can kind of infer electric flux related to the charge inside the Gaussian surface of interest. So this is a full statement of Gauss law, that if you have a Gaussian surface, which means you have a closed surface, the electric flux going through this closed surface equals to the total electric charge inside the surface divided by constant epsilon 0. And what is this epsilon 0? This epsilon 0 is related to Coulomb constant. By this relation, k equals 1 over 4 pi epsilon 0, so epsilon 0 is also 1 over 4 pi k, and you plug in the number of k we learned, we find epsilon 0 is 8.85 10 to the negative 12 Coulomb square over Newton meter square. So electric flux equals the charge you have enclosed inside divided by epsilon 0. This is Gauss law. So Gauss law can help you relate your E to your Q. And we don't need to do any integration if you know how many charges are inside the Gaussian surface. You can directly calculate what would be the electric flux going through the surface. Now in this example, we have charge Q, negative Q. We have surface A, surface B, surface C, surface D. What's the net charge enclosed in Gaussian surface D? There's no charge at all in D, so electric flux going through D is 0 from Gauss law. How about C? You have a positive charge, negative charge, they are equal magnitude, opposite sign, right? So net charge is also 0. So for C, for Gaussian surface C, the electric flux is also 0. Now for A, you have positive Q, so electric flux is Q over epsilon 0. Same for B. Your there is a typo. The electric flux going through surface D should be negative Q over epsilon 0. What is the electric field of a point charge if we use Gauss law? So let's do it for this sphere with radius r. So the area for a sphere is 4 pi r squared times E, and this is electric flux. And why is that? Because your A is in the same direction of your E at every point on the sphere. At every point, dA is perpendicular to the surface. E is perpendicular to the surface. So your dA and the E are always in the same direction. Cosine phi. Phi is 0 everywhere, so give you 1 everywhere. So this is my electric flux. Using Gauss law, it should equals to Q over epsilon 0. Okay, so what does it tell us? We can rewrite it. So E is going to equal 4 pi r squared Q over epsilon 0. And if we rearrange it, 4 pi epsilon 0 Q over r squared, and I know 1 over 4 pi epsilon 0 gives me K. So electric field, the strength is K Q over r squared everywhere on this sphere, which basically this is also Basically, this equation is exactly Coulomb's law. So Gauss law and Coulomb's law actually is equivalent. You can derive each other. You can derive Gauss law from Coulomb's law, or you can derive Coulomb's law from Gauss law, just as we did. And use Gauss law, we can also find out what will be the electric field generated by a infinite known rod carrying charge. So let's say the carry uniform of charge. So the charge density is the same everywhere. We want to find out what will be the electric field generated by this rod at a distance r from the rod to this surface. So first you need to try to think what will be the direction of an electric field on this curved part. So on every part of this curved surface, electric field is perpendicular to the curved surface. Your dA is perpendicular to the surface everywhere too. So for the curved part, E and dA phi equals 0. So cosine 0 is always 1. So it's just the electric flux is going to be simply, let's say, is curved part. The electric flux going in the curved part is simply area of curved part times electric field on the curved part. And there is a symmetry because every point of the curved part it has same distance to the rod. So E should be the same everywhere. And we discussed if you cut this curved part, it's going to give you a rectangle with one length L and one length 2 pi r. So the area of this curved part is 2 pi r L E. And that's the electric flux going through the curved part. And because it's a Gaussian surface, we still need to think about what's the electric flux going through these two surfaces. Now, the area dA, the normal vector of this vector is in the same direction of the rod, which is going to be perpendicular to RE everywhere. So the angle between this cap and E is 90 degree. Cosine 90 degree give us 0 electric flux going through this surface. Let's call it area 1. Phi circle 1 is 0. Same argument, your dA is in the same direction of the rod, perpendicular to RE, equals phi 2 is also 0. So the total electric flux is 2 pi RL times E. It equals the total charge you have inside this Gaussian surface. The length is L. Charge density is lambda. By definition, lambda is Q over L. So your Q is lambda times L equals lambda times L equals Q over F epsilon 0. So now we can solve for E. L kind of cancelled. E equals lambda over 2 pi r epsilon 0 for this infinite known rod. So we have the general statement. The electric field produced by infinite known rod at a point which is distance r to the rod is 1 over 2 pi epsilon 0 lambda over r. So let's do a more concrete example. So that you have charge density 1 microcoulomb per meter, and you want to find out the electric field on one point of the surface. So our first job is to find the electric flux. Electric flux, and we're going to use Gauss law, equals charge enclosed inside divided by epsilon 0. And the charge enclosed inside is lambda times L over epsilon 0. Okay, my L is 1 meter, so lambda times L is 1 microcoulomb. 1 microcoulomb over epsilon 0, 8.85, 10 to the negative 12. Okay, we need to put in the unit. I'm using SI unit, so I know phi is Newton per coulomb meter square. Putting all the numbers, Fn is 1.13, 10 to the 5th order Newton per coulomb meter square. And then I need to find out the electric field, which is, we need to use Gauss law, right? So I already know phi is this number, and I already know E times A give me phi E. So my E is phi E over A of this curved part, and the area of this curved part is 2 pi RL. Area curved part is 2 pi RL. 2 pi times R, which is 1, L is 1. So E is Newton per coulomb. Putting all the number, I find that E is 1.8, 10 to the 4th Newton per coulomb. Okay, the last example, or infinite known sheet of charge, what would be the electric field. So you build this Gaussian surface. Your E is pointing this way everywhere. So this time, your E is in the same direction of your A for these two circle caps. And how about the curved part? For the curved part, your A is perpendicular to the surface everywhere, and your E is only perpendicular to the infinitely known area. So your dA for the curved part, perpendicular to your E. So you don't have electric flux going through the curved part. Electric flux going through curved part is 0 this time. And phi 1, so let's call this one area 1, this one area 2. Phi 1, E and area 1 in the same direction, so you just have E times A1. Your A1 is just a pi r square, and your phi 2 is E times A2, E times pi r square. So the total phi is, you add those three together, equals the total charge you have inside. And you have, so area charge density is charge over area. So your charge is sigma times A. So it should be 6 times A, which is sigma pi r square. And this side is 2 pi r square, because you have this one plus this one. E times 2 pi r square equals sigma pi r square. Pi r square cancel pi r square, solve it. Oh yeah, Gauss law says this is, we have a epsilon 0 here. So we have E, so for E, sigma over 2 epsilon 0. This is an electric field generated by an infinite plane sheet of charge. Conclusion. So let's put it into a numeric example. What's happening if your sigma is 1 microcoulomb per meter square this time? So I can solve for my E is sigma over 2 epsilon 0, 1 times 10 to the negative 6 microcoulomb divided by 2 times 8.85 10 to the negative 12 Newton per coulomb. Plugging all the numbers, I get 5.65 10 to the 4th Newton per